All right, new topic. And this is probably something that even if you had uh, factorial ANOVA in your intro stat course, you probably didn't cover. And that is simple effects. In describing interactions, so far we've just looked at graphs and said, oh, well, this is bigger than this. This one, they look like they're not that different. Of course, that should make us really uncomfortable. It's nice to see things visually, but of course, we want to put numbers on that sort of stuff. A simple effects test breaks down an interaction into smaller components that look very much like simple t-tests that allow us to draw clear statistical conclusions. So we're going to break down our interactions using simpler tests. The biggest issue is how the error term gets addressed. We don't just use straight up normal t-tests because for simple effects, it uses a different error term than we would if we just did a t-test. I'll talk about some of the formulas to give you a sense of this and highlight it going forward. We used to have to do all kinds of calculations of this, but then a package called FIA came out that made it really easy to do moving forward. One thing of interest with simple effects is that they're generally done without any sort of type 1 error control. There's no version of the Tukey test for a simple effects tip, for a simple effects test. And I've heard various interpretations of that. Some people will say, oh, well, because it's a priori, you don't need to do that. But I think the better answer is that's just the way that people typically have done things. And if you're looking for consistency across different statistical applications, you probably are not going to find that. Just lean back and accept the weird inconsistency. It doesn't make much sense to me, but doesn't really make much of a difference. And as I said before, this is really what we were doing when we were looking at the graphs, saying, does the effect of factor A look different at B1 versus B2? We're doing that. We're just doing it with statistical test. So you can see a graph, just to remind, this is from our data. What we would be doing, for example, is asking, does the friendship manipulation differ in the performance goals? Does it differ in the learning goals? And we apply what's essentially a t-test. It's actually an f-test, but just a comparison of those two means in each of the cases. The command here is FIA test interactions. Again, the name of the where you stored your analysis. You have to give it the name of the fixed factor, which was goals manipulation, and then across friendship manipulation. I never remember which is which. So if you want to do it a certain way, you might just have to play around with it. Adjustment equals none. So you could put an adjustment in here. If you're really worried about an adjustment, just evaluate everything against alpha of 0.025, and you'll be fine. It's pretty simple. Looking at performance, we see a significant effect for performance, but not a significant effect for learning. And if we go back to the graph, you can see very clearly the performance is producing a significant effect, learning not so much. Again, we're just putting numbers on this particular on these particular relationships with the simple effects tests. In general, anytime you have an interaction effect, you're going to need to do some sort of simple effects test to follow up. As you're reading research literature now, you'll probably be seeing these a lot more. Now, a couple of interesting things. The sums of square residual here. Just to go back, it's the same sums of square residual as we have for the overall analysis. And that's not a coincidence. We actually set that in that way. The logic being this is just falling out of that original analysis. If you were to just do this with t-tests, comparing just those two, just those conditions, subsetting and doing t-tests, you would have the wrong error term. This doesn't give you eta squared, but we can get that very easily for performance. We can just take our sums of square for the effect and divide that by the sums of square for the effect plus, oh, I'm sorry, they wouldn't have this, plus the sums of square for the effect plus, my bad here, I was doing, I was doing eta squared rather than partial eta squared. There we go. Divided by the sums of square for the effect plus the sums of square residual. And this comes out to 0.08. I didn't calculate it for learning, but it's going to be 0. You can see how small those sums of squares are in relation to each other. So that's eta squared. You can calculate that by hand very easily. It'd be nice if this gave it to you. I don't know why it doesn't, but not a big deal to get it. In terms of the calculations, these calculate these calculate sums of squares based on this formula for a at b1. And you can see the big difference is the sums of squares. All it's doing is focusing on the particular cells that we're interested in. So if we were calculating this for the performance condition, we can see we've got an overall mean of 5.2. So we take 41, we take the sample size of 38, 41 minus 5.2 plus 5.74 minus 5.2, square it, add them up, and that's where we get that sums of square value. And then subsequently, that's where we get all of the other pieces. And we divide by the degrees, the mean square within. And that gives us our f and our eta squared.